so why don't we start with 2744, and then we'll move on to 2745, and so on. Everyone saw the half sheets on the desk, right? Taking an AP Science next year? Yeah. Good. Little. Here. I think this is it. No, this is part for 123. All right, so 2744. Supposed to see the light in a vacuum. It's only 25 kilometers an hour. Find the length of a bicycle. Speed of 20 kilometers an hour is measured by observers in a park bench. Given this proper length. Now, folks, remember, you don't need to follow along. Try to keep it down a little bit so those people that want it are following along can hear. All right. So, all right. And so by the proper length, what they mean is the length in the frame of reference of the bicycle. So, 2744. So what happens to the length of the bicycle as observed from an outside frame of reference? It shrinks. So the length contracts. As the bike moves. And it's probably about all I need for the Y. That's about all I need to understand, really. Looking at, this is pretty straightforward, looking at my equations, I'm going to grab the one about length contraction, which is this one here. And as normal, and I just messed up. I need my Lorentz transformation. Yes, sir. Look in your units folder. Should be in there. The newest equation sheet. In the relativity folder. I'm trying to put it up there. Is it in there? Oh yeah. They're also on the summer. Yeah. So one thing to keep in mind is that, you know, people always sometimes have trouble. Okay, which one is L? Which one's L naught? We know that the length is going to get shorter. We also know that the Lorentz transformation, or gamma, is always, so let's see, V is always less than C, so it's always less than 1. So it's always greater than 1 on the bottom. So the Lorentz transformation is always less than 1, right? And so if I divide by a number less than 1, what happens to my value? It grows. But wait, this isn't always, is the Lorentz transformation always less than 1? Or is it always greater than 1? I'm not hearing any conviction. It's always equal to 1?
Oh wait, no. It's greater than 1. The bottom is less than 1. It's on the bottom. So it's like,
the bottom is always less than 1, but that's on the bottom. Yeah, and that's where it's really, it's best with your mind. So the Lorentz transformation is always greater than 1. And if I divide by a number greater than 1, what do I get? A lower number. So L is always less than L naught So however I look at it, in this case, my L naught is my proper length, my 1.89. When it becomes really confusing, I find, is with the time. Because you think of less time passing, is that shorter or longer, bigger or smaller number. So now it's really plugging in, and I'm looking for L. I have my L naught 1.89 meters, I think. Double check. For me, it's 1.89 meters. My speed of light is 25 kilometers an hour, and I'm moving at 20 kilometers an hour. So that's over 1 over the square root of 1 minus 20 kilometers an hour squared over 25 kilometers an hour squared. I'm going to simplify that algebraically a little bit. 1.89 meters times the square root of 1 minus 20 kilometers per hour, 25 kilometers per hour, quantity squared. And that should help me arrive at my answer. Let's see. And I get 1.13 meters. All right, so the next one that was asked for is 2745, which in essence is the exact same problem that we just did. So this will be good repetition because, again, we're talking about length contraction. It might have thrown some people when they didn't tell you what length they wanted. They said a pure square, which, if you remember, a square is width and its height match. And so the other part to remember here also, and this should be probably part of your why, is that only the dimension in the direction of travel is affected by relative motion. So as they show in the picture here, the height is not changed because there's no relative motion in, say, the y direction, but only the width is because there's only motion in the x direction. So that would be important to have as part of your why. Like if you had a problem like this on, say, I don't know, the final or something, it would be important to show that you knew that only the dimension in the direction of travel is shortened. And then something like the faster the motion, the greater the change. And then we would grab the exact same things in our equations here. The Lorentz transformation and the length contraction. And then, of course, I remember that L is less than L naught. And in looking at my problem, I want 129 centimeters to get down to 87 centimeters. And they asked me to express my answer in terms of C. I'm going to take a shortcut since we just did one of these and write this down like this. Now, by combining the v over the c and squaring the whole term, in essence, when they ask me to leave my velocity in terms of c, they want like v equals 0.8c. Well, if you think about something like that, like let's say that v equals 0.8c, if I want my velocity, that's my velocity expressed in terms of c. So I could think of this as v over c equals 0.8. And so if I solve for v over c, then I found that coefficient, and I've left my velocity in terms of c. All right? So I'm going to actually think about this as solving for v over c, rather than just solving for v. So I'm going down to 87.0 centimeters. I'm starting at 129 centimeters. Square root of 1 over v over c squared. And I'm going to solve for v over c. All right, those right numbers? Yes. All right, and so let's see what that comes up to be. Nice thing about leaving it in terms of c is that if I get an answer greater than 1, I know right away that I've messed something up. And I get 0.545. So my answer is less than 1. I'm pretty confident that will be correct. That's what I've got. I've got to square root my answer. So it should have been, that was the correct answer for v over c squared. I forgot to square root it. So I get 0.738. Now that's correct. Knew it. Thought I got the math one. All right, so we're looking at 2747 as the last problem that was asked. So that's good. Gotten through all of the ones requested. And this one is telling you about you're going on a trip. Folks, remember, you don't pay attention, but just be a little quieter, please. And how time is going to differ from the stationary frame of reference as compared to yours. So you want things like the Earth will stay in the stationary frame of reference. Time will pass slower or faster for the person on the trip? Slower. For traveler. All right, so let's grab some equations about time. I think all of these are about time, right? Yeah, these are all about time. So, who, by the way, who is following along? So just know who to ask questions of. All right, this is all for you then, man. Since no one else needs it. Good. That's excellent. So So we need a Lorentz transformation, and we also need our time. And just like we did with length, remember that this is always greater than, or equal to 1, right? Therefore, t is always greater than t naught, right? So when I'm looking at these, I should always think about which one is less time going to pass it. So you fly your rocket at a speed of almost c for 1 year according to the ship's clocks and calendars. How much time elapses on Earth during the 1 year trip? So more time is going to elapse on Earth, right? Because we're assuming that Earth is in a non-moving frame of reference. So for part B, I'm going to say T is Earth, T naught is ship. And so time on the Earth is going to equal 1 over square root of 1 minus 0.99 c over c quantity squared times time on the ship, which is 1 year. And so I'm going to get time on the Earth, and I'm hoping I'm getting a number greater than 1. If I don't, then I've made a mistake in my mathematics, and I can go back and redo it. And I got 7.09 years, which is greater than 1, so that makes me happy. Let's see if it's right. Yep. So so remember that, let's see, is positive trial part of fast so you train if you're younger than you stay at home since you was born 5 years after you. So then you use these ideas to answer the rest. And I think you can do that.